Dear students, today our topic is Michelson interferometer. Okay, so before going to that, what is an interferometer? An interferometer is an optical device which make use of the interference effects to make some measurements. So we know that interference depends upon the wavelength of the light that is used and also the path difference. So using these two properties, we can use the interference or interferometers to measure the wavelength of the light that is used, or the thickness of a sample that is given, or the refractive index of the material that is given. Okay, so these are the applications of the interferometers, and there are different type of interferometers, and here in our topic or in our syllabus we are given the Michelson interferometer. Okay, so now initially we will see the construction of a Michelson interferometer. So here see the Michelson interferometer. This is the basic construction of a Michelson interferometer. So here see we have a source of light, an extended source of light S. Okay, now then there is a lens, so in order to make the beam parallel, it's an extended source of light, and then two mirrors M1 and M2, and then two glass plates G1 and G2, and then a telescope to observe the pattern or the interference that is observed. Okay, so this is the basic components of a Michelson interferometer. So here see M1 and M2 are exactly perpendicular to each other. Okay, that is one main point. Now see this M1 is fixed on a pitch screw. Pitch screw means you know what is pitch scale, is it? Okay, you have used the screw gauge. So say pitch screw means this M1 can be moved along this particular direction. Okay, so this M1 can be moved, and the movement or that particular displacement of M1 can be measured up to an accuracy of 0.1 micrometer. So that is the accuracy of measurement for the displacement or the movement of the mirror M1. Okay, that can be moved up and down. And this M2 is fixed. M2 is fixed one. Okay. Now this G1 is a glass plate. This G1 and G2 are two optically flat glass plates. Now this G1 is having a coating. It is semi-silvered on the back surface. That is, this surface is semi-silvered. Okay, this surface will be semi-silvered. That semi-silvered means it can partially transmit and it can partially reflect. Okay, so G1 is a semi-silvered glass plate, whereas G2 is a simple plain glass plate. Both are optically flat, and both these will be having the same thickness. Okay, so this is the basic setup for the Michelson interferometer. Okay, now we will see the operation. So how it will work. Okay, now see the light from the source S, that is rendered parallel by using a convex lens. You can say it is L. Okay, a convex lens L. Now this light, when reaches the plate G1, remember it is a semi-silvered on the back surface. So what will happen when it reaches the glass plate G1? A part of this light will be reflected. That means this is the semi-silvered side. So a part will be reflected, and that light will go to M1. Okay, and another part will be transmitted, and that will go to M2. Okay. Now initially assume that this G2, okay, we will come to that. So this will go to M2, and then it will be reflected back. Okay. And what will happen to the light that is going to M1? That will go to M1, and it is perfectly perpendicular, exactly perpendicular, and that will be reflected back. Okay. So see this light then reflected back along the same direction, and this will be reflected back along the same direction. Now this light will reach the light that is reflected from M1 that reaches the telescope along this particular path, and the light that is reflected from M2 will reach here, and it is at 45 degree, so it will be reflected, and that light also will reach the telescope T. This is where the observer is. Okay, so these two light rays will reach the telescope T. Okay, now these two are exactly perpendicular. Okay, remember that. So these two lights, that is the light that is coming from M1 and the light that is coming from M2. These two are derived from the same source, yes. So they are coherent and they will interfere, and you can see the interference pattern by looking through the telescope. Okay, so this is the basic construction. Okay, now I think it is clear. Okay, now see this glass plate G2. This G2 glass plate G2 is called a compensating glass plate. So this is called a compensating glass plate. Okay, so we will see why it is called as a compensating glass plate. See, in this picture we can see that the light that is going towards M1, see the splitting takes place at the lower surface of G2, that means this particular surface. Okay, this surface here is the splitting take place. Okay, now see, so up to this point there is a single ray. Okay, then it will be divided into one transmitted and the other reflected component. Okay, now looking at the light that is going to M1, you can see that this light actually starting from here, the light goes upward, that means then it goes through the glass plate G1. Okay, now when it is coming back again, it passes through the glass plate G1. So the light that is going to M1 passes through G1 twice after the splitting. Okay, so it passes through G1 twice. Now suppose G2 is not there. Suppose it is not there. What will happen? G2 is not there. So what is happening is that this light that is going towards M2 simply goes through air only, then it returns and it will be reflected from the back surface of the G1 itself. Okay, so it does not have to pass through the glass plate, whereas the light going to M1 pass through the glass plate twice. Okay, so there is that makes a huge difference, the path difference, because that is a denser medium. So the path difference between these two rays will be much large. Okay, so in order to compensate that, we introduce a glass plate here. Like this. Okay, having the same thickness as that of G1. Okay, and inclination is also the same, 45 degree. Okay, so now we can see that the light going towards M2 also passes through a glass plate having the same thickness twice, towards and when it is returning. Okay, so this is also now passing through a glass plate or a glass medium twice during its travel. Okay, so that path is compensated. Okay, so that is why this G2 is called a compensating glass plate. Okay, so this is the basic construction. Okay, now see we have to find the condition for interference. See, the condition for interference depends upon the path difference. Okay, so we have to find the path difference. So which path difference? Path difference between the light rays that is going towards M1 and that is going towards M2, or you can say this particular light and this particular light. Okay, so this is the condition, that is what is required. Okay, now see, this is I told you this is a semi-silvered glass plate, and when looking from here you can see M2 because there is a reflection, isn't it? That reflected light is actually what you are observing here. Okay, so since it is 45 degree, you are looking at 45 degree, it is a glass plate, say plain glass, suppose a plain mirror is there. Okay, you can assume like that, a plain mirror, and you are looking at an object. You will get a reflection of an object here by or from the glass plate that is kept at 45 degree. So where will you see the image of this one, this M2 or any object? It seems that the light, see, you are observing or you are obtaining the light along this particular direction. So it appears that M2 will be somewhere here, isn't it? That is called the image or the virtual image. Okay. So it is like you are having a plane mirror or a viewing mirror, and you hold it at 45 degree to an object, then the light reflected from that one, okay, that will reach you, and it appears that this object, the object will be behind the mirror, okay, along this direction, because you are receiving the light along this particular direction. So you will see that the object will be behind, okay. So M2, the image of M2 will be appearing somewhere here, okay. So this distance, okay, this point is M2, you can write it as M2 dash, where M2 dash is the virtual image of the mirror M2. Okay, I think you got the idea. After reflection, it seems that M2 is somewhere here. Okay, now this distance and this distance will be the same. Okay, this optic distance and this distance will be the same. Now suppose, okay, now say you can forget about this side. Now you have a situation when you are observing here, you have light rays that are received from two positions. First is from M1 and second is from M2 dash, where M2 dash is the image, virtual image of M2. Okay, so it appears that you can discard this, or you can forget about this one for the time being, and you have the light that is received from M1 and M2 dash. Okay, now this situation is similar to the case of a thin film. We have studied the case of thin film, isn't it? So we have a thin film. Then suppose there is light is reflected from the lower surface and the upper surface. Okay, like this. Suppose it's a film, thin film of anything. Okay, so any material. So light is reflected from the lower and upper portions. That means the two surfaces. Okay, and see the path difference between the two determines whether you are having the constructive interference or the destructive interference. Okay, here also the situation is the same. See, you are having reflection from two positions M1 and M2 dash. In between there is a air film. Okay, and what is the thickness of that film? You can assume that it is an air film. So what is the thickness? Thickness will be the difference between, suppose this point is A. Okay, so the point where the splitting takes place. Okay, so from here M1 you have one distance, and here M2 dash, it is equal to this distance M2 dash. Okay, so this difference between this AM1 and AM2, that is also equal to AM1 minus AM2 dash, that will be the thickness of the air film. Remember, this is because we are observing the M2, the image of virtual image of M2 along the same direction. Okay, so the situation is similar to the case of an air film trapped between M1 and M2 dash. Okay, now say we have to calculate the path difference. Now assume that, say I am drawing it like this. This is M2 dash and you have M1. This is M1 and this is M2 dash. Okay, I am drawing it like this. The two mirrors are there. Then suppose a light ray is coming from this side. Okay, along this direction. So what will happen? Suppose, okay, in this comparing to this situation, this will be reflected from this one, this side, or the M2 dash, and a part will be reflected from M1 dash. Okay, see, I am taking an oblique incidence, that is a generalization, because see here, this is an extended source, isn't it? So light can be coming from different points. This is an extended source of light. Okay. Now for such a situation, say this is M1 and this one is M2 dash. A light ray is coming. Okay, because all that you are observing is along this particular direction. Okay, because this is a source of light. Suppose you are standing here and looking at the mirror G1, semi-silvered one. You can see that it appears that the light source is also along this particular direction, isn't it? You are standing here, looking at the G1. You will see the image because there is a reflection. Okay, so where will be S? S will be along the same direction somewhere here, isn't it? Okay, the same thing. So here we have S, the source. Okay, and here there is a telescope or the eye of an observer. Okay, so this is the telescope. Okay, now see, this is where this is a telescope. You can say this is a telescope. So this is where you are observing the interference effects. Okay, now see, when it is reflected, see, where will you see the image? You are looking at the mirrors M1 and M2. Where will you observe the image of the source? So that will be somewhere here. You can say, okay, it is here. Okay, same distance you have to draw along this direction. Okay, so this will be the position where you will observe one of the images. And then there is reflection from M1 also. Where will you see the image of that one because of that reflection? We can extrapolate again. Okay, like this. So this is where you will observe the second image. Okay, I think you understand this one. See, okay, for explaining that one, suppose you are standing here. Okay, you are standing here and there is a mirror. Suppose the distance is 1 meter. Okay, so you are here looking at a mirror. Then you see that your reflection will be exactly the same distance behind you, behind the mirror, isn't it? Behind the mirror. Okay, so if this distance is 1 meter, where will you observe your image? It seems that you are standing 1 meter behind the mirror. Okay, so this distance is also 1 meter. Okay, 1 meter. Now suppose you are standing here and the mirror is moved to another position. Suppose this is equal to 1.5 meters. 1.5 meters. So where will you see the image of this one? Again 1.5 meter behind the mirror. Okay, so this is, you will be observing your image here and this will be again 1.5 meters. Okay, so see, this mirror is moved through a distance of 0.5 meter. This is 1 meter and this is 1.5 meter. Okay, and where will you observe the new image? New image will be, see, this is 1.5 meter, this is 1.5 meter, so the total will be 3 meters. This is 1 meter, this is 1 meter, the total distance will be 2 meters. Isn't it? 2 meters. So when this is 2 meter, this is 3 meter. That means the image is moved through 1 meter. And how far you have moved the mirror from 1 meter to 1.5 meter. That is 0.5 meter. So when the mirror is moved through 0.5 meter, the image is moved through double that one. That is equal to 1 meter. Okay. Same principle can be applied here. See, there is reflection from two mirrors M1 and M2 dash. Okay. So the distance between the two is taken as D. The distance between the two mirrors is taken as D. That means the actual M1 and the virtual image of M2, that is M2 dash. So this distance is D. Okay. So due to reflection, you can see the image of the source. Okay. So what will be the distance between the sources S1 and S2? The distance between the two mirrors is D. So the distance between S1 and S2 will be now, what is the distance? That is equal to 2 times that one. That is 2D. Okay. Now you draw a perpendicular from S1 to this particular line. That is the line corresponding to S2. This particular line. Okay. Now suppose This is a telescope. You are observing from here. You are looking at a certain angle. Okay, that is why we are drawing this one. So you are looking along this particular direction, and that direction is or that angle. You can draw a line here. Okay, so this angle, that is the angle of observation. This is the horizontal. This is the angle. Okay, so angle of observation you can draw here. You can draw it. Okay. So what is that angle? That angle will be theta. Okay, that is taken as theta. So here also the angle will be the same. So this is the horizontal line. Okay. So angle of observation is theta. That means what is this angle? You draw a line from S1 to S2. So what is this angle? This angle is also theta, isn't it? So what is this distance? This distance is 2 into, up to this point. That is 2d into cos theta, isn't it? 2d cos theta. So now you can see that from this line onwards, both the rays are having the same distance. Okay. So what is the path difference between the rays coming from M1 and M2 dash? That is between S1 and S2. That value will be equal to 2d cos theta. So 2d cos theta is the path difference between the two rays. Okay, path difference between the light rays coming from M1 and M2. Okay, M2 is taken here as M2 dash. So 2d cos theta is the effective path difference. Sorry, not the effective, the path difference, geometrical path difference is the delta is equal to 2d into cos theta. Okay, 2d cos theta. Now, look at this figure. See, for the light ray that is coming from M2, okay, after reflection, that again get reflected at this point, the lower surface, to reach the telescope T. Okay, so this reflection, when it is coming back, this reflection is from the rarer, this is air here, rarer to denser medium. So what will happen? There is a phase change of 180 degree or pi because of the reflection. That happens only for this particular ray. What about this one? See, for the ray that is going towards M1, the reflection is taking at this particular point. Okay. Now that is, see, when it is coming from here, that is inside, isn't it? The reflection is at the lower surface. So light is going from the denser, that is from glass to air, the denser to rarer. So at that situation, the phase change does not take place. Phase change comes only when there is a reflection from rarer to denser, that means from air to glass. Okay, that reflection you will have the phase difference. Okay, so you have to include that phase difference for one of the rays that is coming from M2. So what is the total effective path difference? We can write it as delta effective, that is equal to 2d cos theta minus lambda by 2, corresponding to the reflection. Okay. Now again remember this theta. See, this is somewhat similar to the case of the equation for the thin film. Okay. But in that case, the equation was 2 mu t cos r minus lambda by 2, where r is the angle of refraction, where in this case theta is the angle of observation. Okay, at what direction you are looking. Okay, that angle of observation. Okay, that is called a theta here. Okay. Now, if this total path difference, so the condition for maximum. What is the condition for maximum? Maximum is that 2d cos theta minus lambda by 2 should be equal to an integral multiple of lambda. Okay, this is the condition for the maximum, interference maximum. Or you can write it as 2d cos theta equal to n plus half lambda. Okay. Now again, what is the condition for minimum? Minimum is minimum. See, the condition is that 2d cos theta minus lambda by 2 should be and so that is equal to 2n plus 1 lambda by 2, isn't it? An odd integral multiple of lambda by 2. Or simplifying, or you can as well write this as 2n minus 1. I already explained you that both will be having the same meaning. Okay. On rearranging, what you will get 2d cos theta equal to n lambda, isn't it? So this gives 2d cos theta equal to n lambda is a condition for minimum or the destructive interference. Okay. So we shall stop here. We will continue in the next class.